Hi, everybody. Let's tackle Chapter 13, Kinetic Theory of Gases. It's pretty fun. Let's start with temperature. Temperature is one of those things that's defined by measurement. Basically, you make a thermometer and you watch it go, and you go, oh, yeah, it must be something called temperature because the mercury in my thermometer is moving up and down as it feels cold and it feels hot. And so let's define it that way. So that's the original definition of temperature. And then later on, kind of in a great triumph actually of 18th century, 19th century physics, they unified. Uh, Physicists were able to unify the notion of kinetic energy with temperature. So basically, it's the same thing as kinetic energy. So it's molecular motions, and they occur in solids, liquids, and gases. But gases are easier, so we're gonna start with gases uh, for this chapter in general. But let's start with solids. So solids will grow and shrink with temperature. So will liquids, and so will gases. So let's flip views here. So let's start in one dimension. Suppose you had a bar of steel or something, and then you heated it up a little bit. So here's my bar of steel. When you heat it up a little bit, it's going to grow just a little bit. So it's going to extend a little longer, and so that length, as the temperature heats up, it's gonna grow. So that little bit extra, we'll call that delta L, where L is the length of the bar, and then L is the so delta L would be basically the length hot minus the length cold. That's probably too tiny to see. So delta L, length hot minus length cold. Just a little bit of length increase there. Simple formula going along. What you need to do is look up an alpha coefficient. We've had lots of coefficients before. And the formula you want is that this delta L is proportional to the length. So as you get a longer bar, you're going to get more change in the length. And it's also got a coefficient. We usually call it alpha. And that's the coefficient of linear expansion. And that's all except for the delta T. So that'll be your change in temperature. This is the coefficient of linear expansion. And that's the length of the bar, L, and then delta L is the change in length, and delta T is the change in temperature. So it's all proportional. This is usually only valid over a narrow temperature range. Basically, used for engineering, it's whatever range is you expect from the weather, and that's perfectly fine. But don't expect it to be. It's not going to go down to absolute zero. It's not going to go up to solar temperatures or whatever. It's a fairly localized coefficient. But at room temperature, you can usually, for any given substance, you can figure out a coefficient of linear expansion. All right, well, let's just do the other geometries. You could have a flat sheet. So you have the area cold, and then when you warm it up, you'll get area hot. And so the question is, if you define a delta area as area hot minus area cold, can we have a formula for that? Yes, you can have a formula for that, and it's delta area is twice alpha times the original area times delta T. 2 alpha, interesting. When we get to volume, so here's our volume, delta volume is volume hot minus volume cold. over some change of temperature. And that's equal to, we usually use a different coefficient. So alpha turns into beta times the volume times delta T. Notice in form, these are exactly the same equations. They're totally easy linear equations. Beta here is usually about 3 alpha. So there's a pattern, 1 alpha, 2 alpha, 3 alpha, and that's kind of clever. Okay, so substances grow usually with temperature. So as you heat them up, they tend to expand a little bit. One exception that's important for us is water. So now we'll flip from that side to this side. Here's a little plot of water with temperatures down here, and freezing is at 0. So at 0, there's a catastrophe, and the water freezes, which totally changes everything. And when water freezes, it does get a little less dense, and that's what's on the y-axis here is density of water, and 1 is here, and just a tiny bit less than 1 is down here. And when that phase change occurs, when the liquid turns to solid for water, the density goes way up. It goes off the charts. So if you imagine cooling down, you start at 12 Celsius, and then 8, then 4, and then 0, and then there's a big jump when it turns to ice. I don't know where it is. It's off screen. But there's this interesting little divot. So you'd expect substances to lower density as you increase the temperature. So they're expanding. They should get lower density as you increase the temperature, and that happens with water up here. So that's the right behavior up there. But then there's this really interesting behavior right next to the freezing point, where water actually turns over, and it's the opposite actually. As you heat it up, the density is increasing. It's actually shrinking a little bit, and that turns out to be super important. So when winter hits, so suppose you had a lake, and then winter comes, and then the top freezes, but ice is less dense, so ice floats. So that goes to the top of the lake. So then the rest of the lake will try to come into equilibrium with that. So the rest of the lake will cool down. So as it cools down, it reaches this interesting 4 degrees Celsius mark. So that's the most dense right there. And that water will roll to the bottom of the lake because it's more dense than everything else. So right there, the 4 degrees Celsius water is more dense than either the 0 Celsius bits or the 8 Celsius bits, and so that's gonna go to the bottom of the lake. Meanwhile, at the top of the lake, yeah, probably more things are freezing at the top of the lake, but that kind of forms an insulating blanket up there. And meanwhile, there's no ice scattered throughout the lake. The ice is all on top of the lake, and furthermore, the water that's about to freeze also goes to the top of the lake. So that means the bottom of the lake is definitely the last to freeze. And that means that fish can survive the winter, which is kind of cool.